Hello students, welcome back to my channel. Today we'll study the topics of jam group theory. That is, we will discuss about some of the results on automorphisms and some important theorems on homomorphism and isomorphism. That is, fundamental theorem of homomorphism, first theorem of isomorphism, correspondence theorem, what is natural homomorphism, Frischmann's theorem. Now, let's get started. Ninth property which we have is on automorphisms. Now, inner automorphism of G is normal subgroup of aut of G. Inner automorphism of G is isomorphic to G modulo center of G. Inner G is equal to identity map if and only if G is abelian. And next property is aut of Zn is isomorphic to multiplication modulo n group. This also holds when G is finite cyclic group because every finite cyclic group is isomorphic to Zn. Now next property which we have is if f is from G to G and G is infinite cyclic group, then since every infinite cyclic group is isomorphic to Z, therefore aut of Z, and we have done that in integers, there are only two automorphisms, that is identity and the zero map is isomorphic to Z2. Next result which we have is aut of G need not be cyclic if G is cyclic. For example, f from Z8 to Z8, aut of Z8 is isomorphic to multiplication modulo 8 group, which is isomorphic to Z2 cross Z2, and it is not cyclic. Twelfth, if aut of G1 is isomorphic to aut of G2, it implies G1 is isomorphic to G2. This is not true. For a counterexample, we will see that aut of Zn is isomorphic to aut of Zm for n equal to 10 and m equal to 5, that is isomorphic to Z4, but Z10 is not isomorphic to Z5. Their number of elements are different. Now some important theorems basically on homomorphism and isomorphisms. First, if G be finite abelian group of order n and map f from G to G defined by f of x is equal to x raised to power m is an isomorphism if m and n का GCD हमारे पास 1 हो. Second, homomorphic image of an abelian group is abelian. Similarly, we have result for cyclic. Homomorphic image of cyclic group is cyclic, but the converse in both the cases are not true. We'll show by an example. F from S3 to Z2, then kernel of F order is 3 such that then it implies kernel of F is equal to A3 because S3 has only one group of order, subgroup of order 3, that is A3. and S of A3 is isomorphic to Z2, which is cyclic and therefore abelian, but S3 is not abelian and therefore not cyclic. Fundamental theorem of homomorphism, which states that let G be a group, N be normal subgroup of G, then G modulo N is homomorphic image of G. Conversely, if any group G dash is homomorphic image of G, then we have that G dash is isomorphic to some quotient group of G. इसकी weaker form क्या है? If F from G to G dash is a homomorphism and onto homomorphism basically, then G dash is isomorphic to G modulo kernel of F. It is a stronger form. Now we will do first theorem of isomorphism, which states that if F is a homomorphism from G to G dash and onto homomorphism where G and G dash are groups such that H is equal to kernel of F and K dash is a normal subgroup of G dash. K is defined as X belonging to G such that Fx belongs to K dash equal to F inverse of K dash, then K is normal subgroup of G containing H, that is kernel of F, and G modulo K is isomorphic to G dash modulo K dash. इसकी visualization देखते हैं. This is G, this is G dash, this is on to homomorphism from G to G dash. Here we have kernel of F equal to H, and here we have K containing a normal subgroup of G containing H such that this whole K is mapped to K dash. According to the definition, K dash is also the normal subgroup of G. What do you mean by natural homomorphism? For N be a normal subgroup of G, then map F from G to G modulo N such that f of x is equal to nx for all x belonging to G is called natural homomorphism or canonical homomorphism of G onto G modulo N. Freshman's theorem states that for H and K be normal subgroup of G such that H is a subset of K, then that K modulo H is a normal subgroup of G modulo H and G modulo K is isomorphic to G modulo H modulo K modulo H. Now, another theorem which we will do is correspondence theorem, which states that if N is a subgroup of G, then there exists one-to-one correspondence, that is one-one onto map bijection between the set of subgroups of G containing N and set of subgroups of G modulo N. ये similar correspondence normal subgroups के केस में भी true है. That is, if N is a normal subgroup of G, there exists one-to-one correspondence between set of normal subgroups of G and set of normal subgroups of G modulo N. Correspondence, one-one correspondence implies bijection, one-one onto map.